Welcome to the deep dive.
Great to be diving in again.
Today, we're getting into something fundamental. Those big, data-heavy applications we all use.
Yeah, how do they actually work under the hood?
Exactly. I mean, think about the sheer number of users, all that data flying around. How do these systems even cope?
That's the million-dollar question, isn't it? And we're drawing heavily from the early ideas in designing data-intensive applications. It's a real cornerstone text.
Right. We had a great chat about this in our machine learning book club recently.
We did, and the book kicks off with three massive concerns: reliability, scalability, and maintainability.
The big three,
Mhm.
essential for keeping any serious data system from, well, falling over.
Pretty much. They're the foundation.
Okay, let's tackle reliability first. What does that really mean in this context? Is it just about avoiding crashes?
It's more than just uptime. Reliability means the system keeps working correctly, doing what it's supposed to do, even when, things inevitably go wrong. Faults happen.
Faults.
And it's not just like life or death systems. Think about your photo storage app.
Oh yeah, definitely don't want that failing.
Imagine losing all those memories. That system needs to be reliable. So it's about continuing correct function despite adversity.
Okay, got it. So what kind of adversity are we talking about? What causes these failures?
Well, the book points out a few main types. You've
Mhm.
got hardware faults, software errors, and us humans messing things up.
Human error,
Mhm.
always a factor. Let's start with hardware though. That seems kind of obvious. Stuff breaks.
It does. Hard drives fail, RAM gets corrupted, power supplies die, someone unplugs the wrong cable.
Right. So what's the fix? Just have spares.
For a single machine, yeah, the standard approach is redundancy. Dual power supplies, redundant network cards, RAID for disk arrays,
Mm-hmm.
basically backups within the box itself.
Okay, that makes sense for one server,
But, and this is a key point, that model gets tricky when you scale out to many machines.
which is basically everything now, right?
Yeah.
Especially for stateless apps.
Exactly. For applications where the server doesn't need to remember specific things about your session from one request to the next, you move towards multi-machine setups. Simple hardware redundancy on one box isn't the whole story anymore.
So what about software then? Software bugs. They seem different.
They are fundamentally different. Hardware faults are usually random and independent. One disk failing doesn't make another one more likely to fail, usually.
Okay.
But software errors, they can be systematic. A specific bug may be triggered by, say, a leap second or a weird input.
Uh-huh.
That bug could potentially crash many machines running the same software all at once. Think correlated failures.
Oof. That sounds much worse. Like a domino effect.
It can be. You can get cascading failures where one system failing overloads another. And there's no simple fix like just swapping out a faulty component.
So you can't just have a spare copy of the software ready in the same way.
Not really, no. The book club really hammered this home. You need much more careful design, thorough testing to find those edge cases, maybe process isolation, and ways to quickly roll back changes.
Right, dealing with the root cause, not just the symptom.
Precisely.
And then humans. We make mistakes.
We certainly do. Operators making errors during patching, configuration changes, routine maintenance. It happens.
So how do you guard against that? Training?
Yeah.
Checklists?
Those help, but a key strategy the book mentions is decoupling systems, designing things so that different parts are relatively independent.
So if someone makes a mistake in one area, it doesn't bring the whole thing crashing down.
Exactly. It limits the blast radius, as you said earlier, and it often makes recovery easier because the boundaries are clearer.
Makes sense.
Okay.
That's reliability handling faults. Let's move to pillar number 2, scalability. This is about growth, right? More users, more data.
That's the core idea. Can the system cope gracefully as the load increases?
How do we even talk about that precisely? What's load and what's coping gracefully?
Good questions. We need quantitative ways to describe load and performance. The book uses Twitter's home timeline feed as a great example.
The endless scroll. What's the load there? Tweets per second.
It could be several things: requests per second hitting the servers, maybe concurrent active users, the ratio of reads to writes, the sheer data volume itself. For Twitter, you might think about posts per second, but also timeline reads per second, which is way higher.
Okay, lots of ways to measure the pressure. How do we measure if it's handling it well? Speed.
Response time is key, yes. But just looking at the average response time can be really misleading.
Oh, why is that?
Because the average doesn't tell you about the outliers, the worst experiences. The book really stresses looking at percentiles.
Percentiles. Like the median.
Yes, the median or P50 shows the typical experience. Half the users get this response time or faster. But you also need to look higher up, like the 95th or even 99th percentile, P95, P99.
So P99 tells you the response time that 99% of users are experiencing or better.
Exactly. It highlights the experience of the slowest 1%. And often, those users experiencing the tail latency are the ones who perceive the system as slow or unreliable.
Why would those tail latencies be so much worse, though?
Several reasons. Maybe those users have more data or their requests just happen to hit a busy server, but a big factor is often queuing delay.
Queuing, like waiting in line.
Precisely. Even if each individual request can be processed quickly, if lots arrive at once, they have to wait their turn. This can lead to something called head-of-line blocking.
Head-of-line block, yeah.
Yeah, where one slow request holds up all the faster ones behind it in the queue. So even if your request is simple, you might get stuck waiting, inflating those high percentile times.
Gotcha, like being stuck in traffic behind one slow driver.
That's a good analogy. And it means when you're load testing, you need to be careful.
How so?
The book points out you need client-side response time measurements, and the test clients should send requests independently, not wait for one response before sending the next.
Otherwise you don't simulate that queuing effect realistically.
Right. You might get an overly rosy picture of performance. You need to really hammer the system, like real users would.
Okay, so measure load carefully, measure performance using percentiles. How do you actually make the system handle more load?
Two main approaches discussed: scaling up and scaling out.
Vertical versus horizontal scaling.
Exactly. Scaling up, or vertical scaling, means getting a bigger, beefier machine, more CPU, more RAM, faster disks, just more power in one box.
Seems simpler sometimes.
It can be, initially, but high-end machines get very expensive, and there's usually a limit to how much you can scale a single machine.
Right, so the alternative.
Scaling out, or horizontal scaling. Distributing the load across multiple smaller, often commodity machines, sometimes called a shared nothing architecture.
And that's how the giants operate. Facebook, Netflix, Twitter.
Absolutely. At that scale, you have to scale out. There's just no single machine powerful enough.
The book club mentioned this is often easier for stateless services.
That's a really key point. If the service doesn't need to maintain ongoing state about the user, distributing requests is relatively straightforward. Web servers, API gateways often scale out easily.
But if it's stateful, like a database.
Now that's where things get much more complex. Distributing stateful data introduces huge challenges around consistency, coordination, partitioning, which the book dives into much later.
Okay, something to look forward to. So that's scalability. What about the third pillar, maintainability? Sounds less glamorous.
Maybe less glamorous than scaling to billions of users, but arguably just as important in the long run. It's about making life sustainable for the engineering and operations teams working on the system.
Keeping things sane, basically.
Exactly. You want the system to be easy to work with over its entire life cycle. The book highlights 3 design principles here: operability, simplicity, and evolvability.
Operability, sounds like. Making it easy to operate.
Pretty much. It means designing the system so the ops team can keep it running smoothly. Good monitoring, easy ways to track down problems, tools for deployment and configuration management, automation.
So good dashboards, good alerts, that kind of thing.
Yes, providing visibility into system behavior. Making routine tasks easy and non-routine tasks, like recovering from a failure, possible without heroic efforts.
Okay, then simplicity. That seems obvious. Keep it simple.
Obvious, but incredibly hard to achieve, especially in large systems. Complexity is a huge enemy of maintainability. It makes the system hard to understand, hard to change, and easy to break accidentally.
The big ball of mud scenario the book mentioned.
Precisely. You want to avoid that. Good abstractions are key here, hiding implementation details behind clean interfaces so engineers don't need to understand everything to make a change. Managing complexity is crucial.
Right. Avoid the mud. And the last one, evolvability.
This is about making the system easy to change in the future, adapting to new requirements, integrating new technologies, fixing problems you didn't anticipate.
Someone in the book club called it agility at a large data system level, which I liked.
That's a great way to put it. Business needs change, technology evolves rapidly, you learn more about your data. The system needs to be able to adapt.
Unlike, say, some older BI systems where adding one new field could take months.
Exactly that contrast. Modern systems need to be much more flexible. You need to be able to evolve the system's architecture and features without massive rewrites or downtime. It's about long-term adaptability.
Okay, so those three, operability, simplicity, evolvability,
Yeah.
they all feed into making the system maintainable over time.
Correct. They make it easier for engineering teams to do their jobs effectively and keep the system healthy and useful.
So just to recap the start of the book, reliability is about working correctly despite faults. Scalability is handling increased load. And maintainability is making it easy for humans to manage and evolve the system.
You've nailed the core concepts. These are the fundamental non-functional requirements that underpin pretty much any serious data system.
And the book then uses these as a foundation to explore more complex topics later on.
Exactly. Part 2 gets into distributed data challenges, and Part 3 looks at derived data and system integration patterns. And as we noted, the very next chapter, Chapter 2, jumps into data models and query languages.
Well, this has been really helpful for crystallizing those initial ideas. It's clear it's not just about code, it's about architecture and trade-offs.
Absolutely. Achieving reliability, scalability, and maintainability often involves balancing competing concerns. Scaling out a stateful system, for example, might improve scalability, but definitely increases complexity, impacting maintainability.
Right, trade-offs everywhere.
And choices about, say, data replication for reliability impact consistency guarantees. It's a complex web.
And these aren't just abstract concepts for giant tech companies. They affect everyday apps too, right?
Totally. Your photo storage, your social media feed, even online shopping carts. Poor reliability, bad scalability, or a system that's impossible to maintain will lead to a bad user experience, lost data, or eventually the service just dying.
So, the next step logically seems to be that Chapter 2 dive. Data models, query languages.
That seems like the plan. It's foundational, too. How you choose to represent your data fundamentally shapes how you build the application and what kinds of questions you can easily ask.
Yeah, the preview mentioned comparing relational document graph models, declarative versus imperative queries. Sounds meaty.
It is. Those choices have really profound implications down the line. Definitely looking forward to unpacking that.
Me too. So maybe a final thought for everyone listening. As you use different apps and websites today, try to think about them through this lens.
Yeah, where do you see signs of reliability? Or maybe unreliability? How do you think they handle scaling when things get busy?
And what might be going on behind the scenes, the complexity being managed, just to keep it all running and evolving.
It's a fascinating way to look at the digital world we interact with constantly. Makes you appreciate the engineering involved.